final speaker before our panel discussion is John Dawson of the Pennsylvania State University, whose subject is At Odds with the Zeitgeist, Kurt Gödel's Life and Work.
Thank you, Dr. Goddard. Before I begin my presentation, I would like to express my thanks to the Institute, not only for inviting me to speak to you on this occasion, but especially for inviting me now almost 25 years ago to catalog Kurt Gödel's papers. It was a once-in-a-lifetime opportunity, an unforgettable experience, and something for which I'm profoundly grateful. We've already heard a good deal about Gödel's work and some about his life, so I'm certainly not going to present you with a chronological account. Rather, I'm going to be talking today about how Gödel was an outsider almost his entire life, and how his work was done swimming upstream, so to speak, against strong countercurrents. Gödel was well aware of that, and I think it accounts for some of his caution in making some of his works public, but it was accompanied at all times by strong conviction. So I attempted, insofar as possible, to interview individuals who had known Gödel, well aware that time was of the essence because many of them were dying off. Among those that I spoke to was Freeman Dyson, and one of the first things he said to me was that he had known several true geniuses during his life, and that he'd come to believe that such people were really different from the rest of us. They're not wired the same in some sense. And he said it's not a matter of degree, they're not just smarter than we are, they really don't think like we do. But Still further down, he says he's often reflected on why Einstein took pleasure in having conversations with him. And he thinks that one of the reasons that was that were the fellow students. This is a picture of him on the right with his brother Rudolph. So just the two of them in the family. And we see this earnest look here. He was early on called Der Herr Warum, Mr. Why, by his parents because he was so incessantly questioning. And what I think is interesting is that this continued. Unlike most children, these sorts of questions that adults find so baffling were something they never ceased to ask. So, for example, children will ask such things as why two events happen to occur together. Now, we as adults would regard this often as a fortuitous thing, but children seek a cause, and Gödel kept seeking causes and kept asking that same kind of question, as we'll see in some of the excerpts coming up. As a student, he went to the Staatsrealgymnasium in Brno. It was a German language school, and fortunately we have some testimony from one of his classmates, which I'll talk about in just a moment. We also know he was, of course, a very good student. He always got the highest grade in every subject. There's only a single exception to that, which you see here. There was one subject in which he only got good instead of very good, but it seems to be a problem that he overcame in rather spectacular fashion later. And here's the testimony from his classmate, a man who ended up living in New York City, Harry Klepetage. And he describes what it was like to be in class with Gödel. He was very withdrawn. He had only one or two close friends, one of whom was Klepetage himself. And notice the last statement that Gödel considered himself always Austrian and an exile in Czechoslovakia. He never learned the Czech language, not even a few words, and was the only student that Klepetage could say that about. So he was certainly a loner, even at that early stage. He went on, as we've seen the slide before, to the University of Vienna, intending to study physics, but quickly changed to mathematics. And there, as we've already heard, he started attending meetings of the Vienna Circle. This is Carl Menger's recollection of his meeting with Gödel and how Gödel behaved at those Vienna Circle meetings. Again, we have a person who's very quiet, who is listening, but only giving very slight indications of whether or not he agreed or not, very cautious in any public expression of his views. And much later, Gödel himself wrote to the philosopher Hilbert that he never agreed with the view of the Vienna Circle, especially the view that Carnap had propounded, that mathematics is simply syntax of language. He did give credit to the Vienna Circle, but said it was just their introduction to the problems and the literature that was important for him. So he's sometimes listed as a member of the Vienna Circle, but really he was even so, an outsider. He listened, but he didn't agree. Now, within the Vienna Circle, there were many disagreements, some of them philosophical, some of them having to do with Neurath's attempt to publish a manifesto for the group, but there were also disagreements on other subjects, and in particular, at that time, some of the Vienna Circle members were quite interested in what we would call parapsychological phenomena, and they believed that it made sense to subject things such as extrasensory perception to scientific study. Others regarded this as a complete waste of time, and there were actually some very strong disagreements on that. Well, Gödel was one of those who believed that it did make sense to investigate such things. That hardly seems surprising for someone who thinks that there is a world out there not accessible by our regular senses. And so, much later, to his mother, who expressed some doubts about parapsychological matters, he tells her his view that, yes, there's reason for you to be skeptical, but the result of the fraud is not that it simulates, he says, but that it masks the genuine phenomenon. So I find this a rather interesting point of view. And then this remarkable statement to his friend Oscar Morgenstern, also in later years, that he thinks that there's a high probability that there exist elementary psychic particles just like elementary physical ones. And it's going to seem a great oddity in the future that we didn't take the trouble to investigate them. So these are views of someone who is certainly thinking very differently than most people, and especially in the 20th century, I think, when we're talking about quantum mechanics and probability theory, to have someone who thinks that chance does not play a role and that there are such forces is very much beyond the ordinary. Of course, for Gödel, mathematical intuition was precisely a kind of extrasensory perception. We have this world of concepts, he believes, that we can access through our mathematical intuition. And this is perhaps one of his most famous pronouncements of that in his paper, What is Cantor's Continuum Problem? Now, Gödel actually attributed some of his success precisely to his Platonistic philosophical outlook and the fact that it allowed him to pose certain questions that others would not consider meaningful. Rudolf Carnap, we've already heard something about, and the differences that Gödel expressed in one of those unpublished papers. I'd like to talk a little bit about Bertrand Russell as well, and also, again, David Hilbert, talking about how different Gödel's thinking was from theirs. So Gödel became acquainted with Russell's philosophy very early. This is now Olgatowski's recollection, that they were studying Bertrand Russell's writings in the Vienna Circle. But Gödel had reservations about that as well, and we know that from a letter that he wrote to Herbert Feigl. He wasn't very impressed with Principia Mathematica. So already by 1928, he'd become acquainted with the work and thought there were some problems with it. Nonetheless, he took that system as the underlying system or the prototype system for both his completeness paper and his incompleteness paper. No one so far has talked much about the completeness paper, but that was Gödel's dissertation, his doctoral dissertation, in which he proved that you could deduce in any so-called first-order theory exactly the statements that hold true in all interpretations of that theory that satisfy the axioms. So this was a very positive result. It was an expected result, but nonetheless quite an accomplishment. And the basic system he used was Principia as well as the system of Hilbert and Ackermann. But, of course, the incompleteness theorem, which he proved very shortly thereafter, and it's unfortunate that in English completeness and incompleteness sound like contradictory terms. They're not such terms in German. The German terms don't have that ambiguity or confusion. The incompleteness theorem, of course, showed that although you can prove everything that holds true in all interpretations of the axioms, you're not capable of proving everything that is true in the one particular interpretation that you're most interested in, namely the natural numbers. And this distinction is sometimes blurred. Now, Russell didn't understand this. This is a remarkable letter that Russell wrote to the late Professor Henkin, expressing his continuing confusion about just what Gödel had done. So it's 50 years since I worked seriously in mathematical logic, and he knew about Gödel's work but was puzzled by it. Made me glad that I was no longer working in mathematical logic. And, if a set of axioms leads to a contradiction, it's clear that at least one of the axioms must be false. Does this apply to schoolboys' arithmetic? If so, can we believe anything that we were taught in youth? So it seems that Russell actually might have thought that Gödel proved that arithmetic was somehow inconsistent. A profoundly mistaken view, of course. Granted that it had been a long time since Russell worked in logic, still it seems rather remarkable. But I think it's explained by what's sometimes called a logocentric predicament, that Russell viewed logic as an all-embracing system, and mathematics was simply a part of it. Well, if you have that view, you can't imagine stepping outside the system and trying to ask the sort of questions about proving consistency, for example, or proving that you cannot prove consistency. These meta-theoretic questions simply are not possible to formulate if you can't step outside of your logical system. And of course, Gödel also distinguished between truth and provability, and that distinction was very unclear for quite some time. Gödel came on this independently of Tarski, but Gödel didn't really have the boldness to proclaim that in print, which Tarski did, and it was semantic concepts were quite disreputable for a while, and it took some courage to go that route. So, like David Hilbert, as we've already seen, Gödel shared this belief that there's no question that human reason can't eventually answer. And this is a very famous statement by Hilbert, which, interestingly enough, he proclaimed just the day after Gödel had given the first very indirect announcement of his incompleteness results. If you're interested and you want to hear Hilbert's ringing statement that there is no ignoramus, you can actually hear this by just going to this website. There is a remarkable recording of the end of Hilbert's address. And when you consider the circumstances that it was at this conference in Königsberg, it's really a remarkable fact that Gödel and Hilbert, in fact, agreed on this despite the incompleteness theorems. Now, many of the facts we know about Gödel are based on letters that he did not send or forms that he filled out but did not return. And in this case, a graduate student at the University of Northern Iowa queried Gödel about how he came upon his incompleteness theorems. And it's clear from this that although Gödel was an outsider in many ways, he was not an iconoclast. He was not trying to upset things. He was, in fact, trying to advance Hilbert's formalist program. What he intended to do was reduce the consistency of analysis, or second-order arithmetic, to that of arithmetic itself, following Hilbert's program, this sort of bootstrapping program for consistency. But he came to realize that the sticking point was that the notion of arithmetic truth is not definable in arithmetic, unlike the notion of provability, and therefore recognized the fundamental distinction between the two. Here is this draft of a letter, which he never actually sent, but he was stimulated to draft the letter. So if you look at the end of it here, or the bottom of the first page, the occasion for comparing truth and demonstrability was an attempt to give a relative model theoretic consistency proof of analysis in arithmetic, which leads almost by necessity to such a comparison. And that thing that looks like the universal quantifier is actually Gödel's insertion symbol. So if you go to the next page, this is sort of the continuation as to the question of their arithmetical definability. Now, crossed out apparently because he regarded it as something that might be a little risky to say. However, in consequence of the philosophical prejudices of our times, nobody was looking for a relative consistency proof because it was considered axiomatic that consistency proof must be finitary in order to make sense. And secondly, a concept of objective mathematical truth, as opposed to demonstrability, was viewed with greatest suspicion and widely rejected as meaningless. This may seem very strong, but in fact, there are other statements by Carnap, for example, in his intellectual autobiography, that there was indeed a great deal of very strong opposition to the idea that you could argue semantically and not be on slippery ground. So we know that Gödel was aware that he was at odds with the zeitgeist, and the paper that Professor Burgess has mentioned earlier, The Modern Development of Mathematics in the Light of Philosophy, which again he did not publish during his lifetime, is perhaps his most polemical statement of that. Some people have said that Gödel misjudged the strength of the opposition to his views, but I think it does have to be considered in the context of the time. And if you look at the history of logic in the 20s and early 30s, I think it becomes a little more understandable. Now, very early on, in the introduction to his doctoral dissertation, Gödel had already made some philosophical claims which were actually dropped from the published version of the dissertation. And one of those, he disagreed with Hilbert's belief that if you proved that a set of axioms was consistent, that you would thereby establish that there must be some interpretation in which those axioms held. The dissertation actually showed that that was correct, as long as you're talking about so-called first-order theories, in which the quantifiers range only over the objects of your domain of discourse. But if you allow your quantifiers to range over subsets of your domain of discourse and formulate the Peano axioms, for example, in this second-order formulation, then the second incompleteness theorem shows that Hilbert's belief is false, because there's a well-known proof that Peano's second-order axioms have only one model, namely the natural numbers. But assuming that that theory is consistent, the second theorem says that you cannot prove the consistency statement, so you're free to add not only the consistency statement, but it's undecidable, so you could actually add the negation of the consistency statement. That would give you a theory in which no contradiction is provable, but which has no model. So for second-order theories, Hilbert's belief that proving consistency was equivalent to proving the existence of a satisfying interpretation is false. Now, Gödel's results were so striking that, of course, he was invited to come to America. We saw a picture earlier of the Institute for Advanced Studies' first home. Before Fold Hall was built, the old Fine Hall, now Jones Hall on the Princeton campus, was shared by the Princeton mathematics faculty and the original Institute for Advanced Study faculty. Gödel was here in the Institute's very first year of operation, the fall of 1933, and was there in that building. And there he met Alonzo Church, the eminent logician on the Princeton faculty. And Gödel asked for a semester to improve his English before lecturing on his incompleteness results, so he began lecturing on them in the spring of 1934. And in those lectures, he introduced this very important notion of general recursive function, which then the following year, Church used in formulating his famous thesis, which asserts that Gödel's notion of general recursive function, which was actually based on some ideas of the French logician Jacques Bertrand, that it captured the informal idea of effective procedure. And of course, this is a fundamental result for the development of recursion theory and computer science. What's interesting, though, is that Church had already formulated a system of his own, the so-called lambda calculus, and he could very well have formulated his thesis in terms of his own notion of lambda definability. But he chose not to do that. He chose to put forward the thesis using Gödel's notion, and there's been quite a bit of literature recently about that, why that might have been the case. And more importantly, Gödel was one of those who definitely did not believe the thesis. He didn't think it was at all likely that his notion really captured the informal notion of affected computability. And it took Alan Turing's work to convince him of that. Turing was actually here in Princeton also in 1936, so just a couple of years later. Unfortunately, he never met Gödel because by that time Gödel had been incapacitated by mental illness and was not on the scene. We know that Gödel admired Turing's analysis, but nonetheless, again, he certainly didn't agree in toto, because he went on in later years to dispute Turing's contention that mental procedures couldn't go beyond mechanical ones. It's a very interesting, very short remark in which he claims that our mind is not static like a Turing machine, but is constantly developing, and continued to believe then that there aren't these mathematical questions that remain undecidable. So we've already heard that despite his own work in set theory and the later work of Paul Cohen, unlike Cohen himself, Gödel did not think that the question of the truth or falsity of Cantor's continuum hypothesis was something that simply had no answer, but rather that the axioms we have are not sufficient to settle it, and therefore we have to find other means or other axioms, because he really wanted to know whether it was true or false, not whether it was provable or not in a particular axiomatic system. So already in 1934, Gödel had begun to exhibit some signs of mental illness. He kept meticulous records of his dietary habits, of his body temperature. There are records of a decade or so of his daily body temperature. He was obviously hypochondriacal, and also indications of paranoia, especially a fear of poisoning, which in the end would be the cause of his death. Either being poisoned by something that he ate or by poison gases that he believed might be escaping either from his refrigerator or from the heating system. We have a statement from the former IAS director, Frank Adelot, as to the severity of those beliefs. This is a letter that Adelot wrote in an attempt to get Gödel declared 4F by the American Draft Board. Interestingly enough, Gödel was not exempted from military service by the Nazis, who found him fit for garrison duty. And it's an interesting question of whether they were really aware of his institutionalization for mental illness. But in 1935, Gödel came very briefly to the Institute. He had already had a bout of mental illness, but he thought that he was okay again. But he was only here for about a month. And another coincidence having to do with the date, November 17th, is that it was on November 17th, 1935, that Gödel turned in a letter of resignation and returned to Austria because of his recurring depression. Well, after he did so, you can see the description that he was in two different sanatoria, the one at Purkersdorf and the one at Reckerwinkel, which is the largest mental institution in Austria. And in particular, when he was at Reckerwinkel, the situation was quite serious. He would only eat things that were prepared and brought to him by one particular woman, whom he later married, and then only on the condition that she eat with him from the same plate with the same spoon. And apparently even his mother was, at that time, actually afraid of him. Fortunately, the treatment was effective, and it was a very restful atmosphere. You saw this slide earlier in Professor Zygmunt's presentation. This is the building at Purkersdorf, a suburb of Vienna. Very famous building architecturally because it was designed by Joseph Hoffmann. And the building still stands. It is now an old age home, and I had the privilege of going to see it earlier this year when I was in Vienna. But it was a very restful place, and it seems to have had salutary effects on Gödel's mental health. The other thing that certainly helped him, and I think probably is the most critical factor, is that he married Adela Porkert. Again, you've seen this picture before, the wedding portrait. He had gone with Adela for quite some time before that, but did not marry her until after his father's death. His parents were quite opposed to the match, so once again he was going against prevailing opinion in marrying someone who was a cabaret dancer, who was older than he was, who was Catholic, a divorcee, and who had a prominent facial birthmark, which doesn't show in this picture because it's turned away and obscured by cosmetics. But I think Gödel really did play a critical role in his life by literally calming his fears and keeping him alive by testing his food for him. And it was an enduring marriage. Now, the other thing that, of course, saved him literally was his emigration to the United States. He went back in 1939. He had left Adela in Austria while he came once more to the Institute to lecture on his set theoretic work. When he went back, the Anschluss had occurred, so Austria was now under Nazi control, and he's suddenly called up for a military physical, and that's when he's declared fit for garrison duty. How he managed to get out is a complicated story of a lot of bureaucratic red tape. He was able successfully to claim that he had no way of making a living in Austria because his position as a docent was no longer available to him. The so-called docenter, the right to teach, had been abolished by the Nazis and replaced by this docenter of the New Order that Professor Zygmunt already mentioned. And so he had to be vetted for that to make sure that his opinions were in sympathy with the Nazis. So he argued that he had no way of making a living in Austria, but he did have a standing invitation from the Institute. And despite the fact that he had been declared fit for garrison duty, he was eventually released. Unfortunately, he had to travel the long way around. It was considered too dangerous to cross the Atlantic at that point. So his exit papers required that he go by the Trans-Siberian Railway. So he went all the way across Russia and Siberia, then took a ship to Japan, waited there for a couple of weeks for a ship to come from Shanghai and pick him up and then take him to Hawaii and eventually to San Francisco, where he boarded a transcontinental train and then came to Princeton. It's a very long journey. For someone of frail physical and mental health, you wouldn't think that he did very well, but here's a picture of him and his wife on board, and he looks like he survived it very well indeed. So he came to this haven here in Princeton, where he had no specific duties, and surprisingly, once he got here, he turned his attention largely away from mathematical logic to philosophy and to, surprisingly enough, relativity theory. And this is an aspect of Gödel's work that's often overlooked. No one has talked about it here, and indeed at the memorial service for Gödel, it was regarded by Dr. Kazin, who was then the IS director, as not worth a talk. It's rather surprising because Gödel showed that Einstein's equations for general relativity theory can be interpreted in such a way that the universe rotates, and that makes possible time travel, in theory, into the past, with all kinds of philosophical problems that show the difference between causality and temporality. It's a very paradoxical sort of universe, and I think is now regarded as interesting from what it shows as a possibility rather than a reality. But Gödel hoped that maybe astronomical evidence would show that our universe really is of that sort. And Dyson in particular remembers being queried by Gödel on several occasions about the latest data on orientations of galaxies, because if there had turned out to be a preferred direction for orientations, that would be evidence in favor of rotation of the universe, and this kind of time travel then would become possible. Gödel's original model was in conflict with the observed redshift, but his later models were not. And so this is something that has largely been overlooked until quite recently. And very recently, there have been a lot more interest among physicists, I think, in this strange type of model. Well, here was Dyson's opinion at the time when he met Gödel. So, aside from describing him as pathologically shy, he says, the interesting thing to me was what Gödel's doing and proposes to do in the way of research. He describes Gödel's discoveries up to that point. With the whole of mathematics to choose from and his unrivaled talents, I was very curious to know what such a man would choose to do. But the answer, when it came, was completely baffling. Turns out he spent the last few years working in physics on problems of general relativity theory. And he goes on to explain why this seems so strange, why it's such an unfashionable pursuit. Actually, he wasn't really working in collaboration with Einstein. Rather, there was another volume in the Library of Living Philosophers, one devoted to Einstein, and Gödel had been invited to contribute a paper. And his original idea was to contribute a very short paper comparing the notion of time in relativity theory with some of Kant's ideas on time. But as he began studying it, he made this discovery that there were these strange models in which time travel was possible. So, among other things, this shows that Gödel was far more than just a logician. He was a very talented mathematician, and he certainly knew his differential geometry. The papers are not easy reading. You have to be well acquainted with that field to understand them. He gave a talk on his work at the Institute, and apparently it bowled a lot of people over because everyone was expecting a talk on some logical topic, and instead it was this lecture in differential geometry. At any rate, Dawson certainly thought that it was a very strange thing for Gödel to be working on. And a final example of this sort of unfashionable pursuit is Gödel's proof of the existence of God, which is a formalization in modal logic of an argument traces all the way back to Anselm, but in particular an argument due to Leibniz. Gödel was very much interested in Leibniz's philosophy, and so he felt that it would be possible to formalize some of Leibniz's ideas. But because this was a theological subject, he was very cautious about this, said very little about it during his lifetime, and although word of it sort of leaked out, it was only after his death that details were really made public. In fact, when I was cataloging Gödel's papers, I realized that there was some concern among the triumvirate of mathematicians that were in charge of my work, Professor Burrell, Professor Bombieri, and Professor Milner, that there might be some things in Gödel's Nachlass that needed to be restricted, that scholars would not be allowed access to. And it quickly became apparent that this was the primary thing they were thinking of. And it took some persuasion on my part to convince them that while mathematicians may think it's silly to try to prove that God exists, philosophers certainly don't, and that this was something of real interest in philosophy. And so eventually, unlike Russell's papers, where, as you may know, large segments are embargoed and you can't see them because the contents are libelous, or at least were libelous to living people, you can see everything in Gödel's Nachlass. There aren't any restrictions on that. Now, Gödel's strange interpretations, of course, carried over to his daily life as well as to his work. In particular, his search for hidden causes. We can see that in many places, in his letters to his mother especially, but in recollections of other people and in Oscar Morgenstern's diaries. So let me just give you a few examples of it. This is a letter that he wrote to Carl Menger. The circumstances are that Gödel has just gone back to Austria a couple of months before, after teaching a semester at Notre Dame. He came to the Institute to talk about his results in set theory in the fall, and then he went to Notre Dame at Menger's invitation to basically do the same thing. At the end of that time, he went back to Austria to rejoin his wife, and so it's at this time that he receives the notice to report for his physical for the Nazi armed forces. There's all kinds of upheaval going on. So he's writing to Menger to say, since the end of June, I've been back in Vienna again, and in the last few weeks I've had a lot of running around to do, so that unfortunately it wasn't possible for me to send you some notes about the colloquium which Gödel had taken over. And then he wants to know how the exams for his logic course turned out. Well, note the date when this is written, August 30th, 1939. 2 days later, the Nazis invaded Poland. Menger's comment was that he thought this letter set a record for non-involvement on the threshold of historic events. So it ties in with the coffee is wretched remark. He seems to be unaware of what's going on. Now, another interesting letter, Hans Turing was a physicist at the University of Vienna from whom Gödel had had some courses. When Turing learned that Gödel was coming to the United States, he took him aside and told him that he was very worried that the Nazis might develop an atomic bomb ahead of the Allies. And he wrote Gödel that you were not the only one that I mentioned this to. I knew of several people that were going to America by different routes, and I asked each of them to try to get in contact with Einstein to warn Roosevelt of this possibility. Well, by the time Gödel arrived in March of 1940, the famous letter that Einstein wrote to Roosevelt had long since been delivered, so Gödel had no influence on that. But Turing didn't know that, and so at this point, Turing was an old man, he was in bad health, and he wanted to know before he died, did you do it? Did you give the message to Einstein? And so Gödel begins by saying, well, I'm sorry to hear from your letter that you had a stroke and that you have a continuing disability as a result of that, and he wishes him the best for the future. As far as your question is concerned, all I recall is that I just brought your greetings to Einstein. He says at the time, around 1941, I'd lost all contact with physicists, and at that time I didn't know that there'd been success in achieving a chain reaction, so that although I heard about those things later, I was very skeptical, not on physical grounds, but on sociological grounds, because I thought that that discovery would only occur toward the end of our culture period, which presumably lay in the distant future. Very Spenglerian sort of view of when things happen. In another letter, he said it wasn't time for a third world war because there hadn't been enough time go by, and he talked about how much time went between the first and second. Here's another unusual point of view. I don't think too many people felt there was any mystery about Franklin Roosevelt's death. It was known that he was in very ill health for quite some time. But Gödel found it very problematic. Similarly, one of the events that occurred, of course, in 1953 was the execution of the Rosenbergs, and Gödel's view of the responsibility of their defense team for that execution is certainly something that I think is very different than the view most of us would have had. Now, here's an example of his finding something striking about a coincidence. He finds it interesting that within half a year, both of Einstein's principal opponents died. I have no idea where the probability of 1 in 2,000 comes from. And this is someone, of course, who doesn't believe in chance, so this is a statistical probability. It's not a... Now, one of the most curious recollections is this one from Carl Menger's Memories of Gödel. Both Morgenstern and Gödel were actively trying to get some of Leibniz's papers, copies of them, from the archives in Hanover, transferred to the United States. A curious thing that they discovered early on was that copies had supposedly been sent and deposited at the Library of Congress, but the Library of Congress had no record of them. They never did figure out what happened to them. So Gödel even considered going to Germany at one point. Eventually the papers were transferred through the efforts of some others. But at any rate, Gödel felt even so that some of Leibniz's ideas had been intentionally suppressed. So this was a conversation that Menger had with Morgenstern, and Morgenstern is telling him about they went to the Princeton Library, and Gödel was going to demonstrate the basis of the evidence for his belief. So he piled up books and articles that appeared during or shortly after Leibniz's lifetime. They contained precise references to the writings of his that were published. And then on the other side, he had those collections. And here's what happened. In some cases, neither on the cited page nor anywhere else was there anything by Leibniz. In other cases, the series broke off just before the cited volume, or the volume ended just before the cited page. And in other cases, the volumes that supposedly contained the writings never appeared. And no one seems to have given an explanation for this. So it seems strange, but maybe Gödel was onto something. So I don't know if there's any Leibniz scholars in the audience, but it'd be interesting. There's plenty of notes in Gödel's Nachlass about Leibniz. All you have to do is master his shorthand, and you can start looking at that. Well, as I started by saying out, geniuses don't think the way the rest of us do, so it's probably presumptuous to try to completely fathom the mind of someone like Gödel. I think one of Solomon Pfefferman's remarks in the collected works is worth quoting, that with any extraordinary thinker, the questions we'd most like to see answered are the ones that prove the most elusive. So what we arrive at is just a mosaic of particularities from which hopefully some patterns will emerge. But there's one comforting respect in which Gödel was like the rest of us. He too had trouble following lectures. So I hope he wouldn't have had trouble following today's lectures, and I thank you for your attention to mine.
Well, now we come to the last part of our program, panel discussion, which will be moderated by Juliet Kennedy of the University of Helsinki.
All right, is this? Yes. Okay, well, welcome everyone to the panel discussion segment of the program. We've heard some very, very interesting talks, and I'm sure you all have, or many of you may have some questions. So I would like to start by taking your questions. Perhaps the panelists have questions for each other, and I have questions for them too. But I'd like to start with, yes. I think maybe John Burgess would be, since you covered the philosophical work.
I've heard of hearing, and I thought they were going to have microphones out in the audience.
Oh, yes, that's right. So the question was, what was Gödel's familiarity with Eastern philosophy, and his, did it have anything to do with his statements about coincidence and that sort of thing?
Well, that's a biographical question, so maybe...
Oh, all right, so...
Let me respond to it to an extent. Gödel certainly had a strong interest in comparative religion. There were many books in his library having to do with all sorts of religions. I can't tell you specifically about the Eastern religions, to how much attention he paid to them, but certainly he had a broad knowledge of religion in general. He did have some notes having to do with Western religions that are, I don't really know what the basis of it was, but he had a whole notebook, for example, where he had histories of the saints and these long lists. It's shorthand material, which we've never transcribed because it didn't seem of major scholarly interest. But yes, it's possible that this might have had some influence on him, but I certainly can't say for sure.
I would expect that he'd also have some knowledge by way of Schopenhauer. He probably, that was a standard.
Right, that was an interest. Yes, in the corner. Hold on a second. There's a microphone coming. Okay, could you stand up, please? Ask your question.
If I may address this to John Burgess, these are the two questions. The first question is, if the Gödel's incompleteness proof is for number theory only, does that mean that you're definitely sure that other branches of math will not be over-encompassing and therefore might be more complete than number theory, which is incompleteness proof is? The second question is, if I get it correct, and I might not have, if the completeness theorem of Kurt Gödel was about you can deduce all possible logical statements from an axiom, is he trying to say that there is no such thing as a super axiom where he can deduce all possible logical statements from that super axiom, and therefore, like if the two axioms that he's comparing to see whether they're equal or not to each other, if one of them does not belong to that set of deduced logical statements from that super axiom, which is supposed to or not encompassing the two axioms of a lower level that he's comparing at, and it's incompleteness theorem. That's my second comment. And the last one.
Why don't we stop there, and you can ask your next question at a bit later. Yeah.
Repeat to me the first question.
Okay, can you repeat your first question? There's two very long questions.
The first question is about his number theory. Incompleteness uses number theory, the field of number theory, to prove incompleteness, whether you can tell a mathematical statement to be false or true. Are other areas of mathematics more encompassing in the fact that they might not be mapped directly into number theory proof that he's doing? And the second question, if you want.
Okay, so let's.
Okay.
And
that question was addressed. There's a famous monograph of Tarski, Mostovsky, and Robinson, which is about putting the Gödel theorem in the most general form. So if you have a theory that's not just about the natural numbers, but it's about real numbers or sets or something like this, so long as it's possible to translate the number theory in a certain sense into that theory, the same incompleteness phenomenon is going to arise. So the phenomenon arises in all mathematical subjects.
Saul may also want to comment on that, since you've done significant work on the generalizations of Gödel's
The problem is I didn't really hear the question.
On the generality of the theorems, do they only apply to arithmetic, or are there other systems that they apply to?
Oh no, as John explained, it's so general one can hardly think of any further generalizations these days. People still find little things that they can do to add to it.
Yes. Right. Okay, and your second question was?
And the second question was, if the completeness theorem says that you can deduce all possible logical statements from a hypothesis or an axiom, and therefore if incompleteness says that you cannot compare two axioms together, I'm twisting what he said a little bit or translating it. If you cannot compare two axioms or two questions to see whether they're equal to each other, a different form of the incompleteness theorem, then is he trying to say that there is no super axiom that can describe all the possible logically deduced statements from it, and therefore these two statements that he's comparing in his incompleteness theorem would not both belong in that set of deduced statements from that super axiom?
Why did you take this one?
Like you, I didn't understand it. I think it's best to take it online because the other, it's just too detailed for me.
Yeah, I think what you're asking about is the meaning of the completeness theorem, and I think well, as I understood the question, I think that's involves some quite delicate definitions and so forth.
Well, there's a terminological
perhaps take
issue
us a far afield. But I think we should move on. A question here? Yes?
Yes, name is Vernon. So I think that it should be mentioned in the connection of the previous question that the work of Tarski on the arithmetic of reals, which Tarski proved that has a complete axiomatization and is decidable, and that has led to a really big kind of industry in logic. And there's a famous Tarski's question whether the arithmetic of reals with exponentiation is decidable, which and complete and axiomatizable, and depends on the number theoretic Chanuel conjecture. But this leads me to the question of the relationship between Tarski and Gödel. In some sense, Tarski is also one of the giants of logic, and but he seems to have gone somehow completely different route and led to a different kind of school. That's how I feel anyway. But I would like to ask Professor Pfefferman, and how did Tarski and Gödel know each other's work well, and how would you compare their impact in mathematics and logic?
Did Tarski and Gödel
meet each other, and how would you compare their impact in mathematics?
Oh, well, they certainly met each other. Met each other rather early when Menger invited Tarski in 1930, I think it was, to speak at Menger's colloquium in Vienna. And at that time, Gödel was able to communicate his completeness theorem. And shortly after he got his incompleteness theorem, Tarski learned about it and was one of the first to give a public exposition of it in Warsaw. And they met again several times in the 30s, in one place or another, and again later in life when both had come to the United States. As far as their intellectual relation is concerned, I think it's quite interesting because contrary to their apparent philosophical views, Tarski believed that set theory is not about a Platonic reality. He believed it's a kind of a game. It's a game that he enjoyed playing, but he believed that one ought to use set theory to the fullest in pursuing his conception of metamathematics, use of mathematics to study mathematics, but not in pursuit of Hilbert's program, but in pursuit of things like model theory, and which has many applications to mathematics. Whereas Gödel, who did have this Platonic view, in his actual practice, hewed very much to the Hilbert strictures, that as much as possible he stated results that could be read entirely as finitistic statements, such as his proof of the consistency of the axiom of choice is not about the truth of the axiom of choice, but simply a statement, if the axioms of set theory are consistent, then they remain consistent when you add the axiom of choice, and the whole proof of that is given in a very finitary way. So in a way, each of them acted in their practice, as far as logic is concerned, in a way disjoined from their philosophy. And I thought that was interesting.
They also remained friends throughout their lives, and it was observed after the volume of the fifth volume of Gödel's collected works came out that of all the correspondents with whom Gödel corresponded in German, Tarski was the only one with whom he was on a due basis.
Yes, in the back. Oh, I'm sorry. Can you wait for the microphone? I keep forgetting.
With respect to his completeness theorem, did that apply to systems which included arithmetic, or in which case wouldn't it be a contradiction? That completeness means you can prove everything you can formulate, isn't it?
No, there's two different senses, and that's what I was trying to allude to in my remarks. His dissertation, which was the completeness theorem, uses completeness in a semantic sense, that you can prove anything that must be true in any interpretation that satisfies the axioms. The key there is any. If, however, you're trying to prove something that's true in a particular interpretation, such as the natural numbers, you may not be able to if that statement is false in some other interpretation that satisfies the axioms. So the incompleteness theorem says that there are statements that are true in the natural numbers which will not be provable. And one way to see why they're not provable is that there are other non-standard interpretations of those axioms in which that statement's false.
But it wasn't disprovable either, was it? You couldn't decide it. This,
Yeah, there are statements that are neither provable nor disprovable because neither the statement nor its negation is true in all models that satisfy the axiom. Some satisfy one and some satisfy the other, and therefore you can't prove either.
I think, as John Dawson said, the completeness theorem and the incompleteness theorem are not negations of each other. It's an unfortunate coincidence.
That's a problem in English
terms.
and not in German. In German, the term for completeness is Vollständigkeit, full standingness, and the term that Gödel uses for incompleteness is, it has to do with what he calls Entscheidungsdefinitheit, which basically, Entscheidung means decide or decision. And so, really it should be called the indecisiveness theorem, not the incompleteness theorem, if you want to translate it.
Yes, in the back?
Well, a twist of that is that the incompleteness theorem does imply the incompleteness of second-order logic.
Yes.
Yeah, so in the other sense.
Yes, in the current practice of theoretical mathematics and in the current practice of theoretical computer science, how much impact does the incompleteness theorem actually have?
Maybe that's a question for Sol.
So, what's the significance of the Gödel incompleteness theorem for mathematics and for computer science? Is that?
Yes.
That's the question. Yes. So I was rather brief about that in my lecture, but what I tried to say was it's tantalizing for mathematics, but what mathematicians would like to know is of specific problems that they've thought about that have remained unsolved in some cases for hundreds of years, whether it's because of Gödelian phenomena in some way or other. And so far, there's no specific evidence to that effect. On the other hand, logicians are working away producing statements which are of a character like these unsolved problems and showing, John Burgess mentioned work of Harvey Friedman that show that combinatorial problems that are rather like problems that have been considered by mathematicians can't be solved unless you assume very, very strong axioms of set theory. What the significance of that is for everyday mathematics is something I can't comment on. As far as computer science, I think Professor Vidgertsen should answer. But I do want to say something before I turn it over to him, and that is Tarski's decision procedure has been mentioned for the real numbers as an example of positive case, but it's been proved that in effect it's exponentially complicated to carry out in general, and so it's not feasible. But there's a strange phenomenon, and that is that there are computer programs that are being used in Mathematica, for example, that employ Tarski's procedure, and for the kinds of problems that people ask, like how many roots does a given polynomial have, and if, say, polynomial degree 5 or 12, fairly low-level problems can be run efficiently on a Tarski-like decision procedure, even though we know, in principle, that overall these problems can't be solved in a less than exponential way. So that's one thing. The other remark I wanted to make is about the P different from NP problem, that probably the solution to that problem is going to be as difficult as as anything we've seen. No doubt Professor Vidgertsen has worked on it, and the difficulty of solving it. So here's an interesting case. We want to show that problems in general are difficult to solve, problems of a certain kind. But the proof of that is going to be even more difficult.
I completely agree with that, but let me answer not on the effect of completeness as I view it on computer science, but rather on mathematics. I think that the effect is huge and is growing if you take the interpretation that the real question is about what knowledge is tractable, what knowledge is practically achievable, and maybe the gap between polynomial and exponential is not the right gap to look at, but it's a good gap to look at. And you can see, those of you who look at actual working mathematicians' problems in algebra, in group theory, in even some in analysis, people starting to realize that the structures they are trying to understand in general are just not yielding. In particular, knots is an excellent example because I told you, and it's well known that knots are decidable. Also, the theory of the reals of Tarski is decidable, but people run into problems like the one you mentioned for reals or for giving invariance to knots. And they even start to realize that the reason they can't access these structures is because looming in the background, you can formulate computational problems, even though they are not interesting per se in computation. There are computational variants of their structural problems which turn out to be NP-complete or harder. And NP-completeness results in mathematics are, a growing literature, and this justifiably serves these particular mathematicians to lower their expectations as to exactly how much they should get out, to what extent, to what degree they can understand a particular mathematical structure. And this is quite pervasive today, and it will even grow. So I think the impact of, the way I view Gödel's question is trying to delineate what we can access, what knowledge we can access from what we can. Of course, he started with decidability versus undecidability. Then later in life, he realized, I wish he worked on it more, that you should really look at the time it takes rather than just whether it's finite time. He realized that the question lies closer to how to even talk particularly about factoring integers and determining the primality of numbers in the same letter to von Neumann. So he knew what he was talking about. He knew these are problems mathematicians cared about. The impact of trying to understand the limits of current techniques in this setting, in this computational setting, does and will have influence in mathematics.
I'd like to add to that. The remark was made earlier that the undecidable statement is one that's cooked up and that there's disagreement on whether there's any natural examples of that. There's a similar phenomenon in linear programming where for a long time the simplex method was the only method that was known, and it's known that the simplex method is not polynomial time. But the examples that show that it's not polynomial time are also cooked up, and no natural example of linear programming has yet come along in which the simplex method is not polynomial time. Subsequently, there were two methods, the Haitian algorithm and the Karmar-Kar algorithm, that are provably polynomial time, but on all practical examples, they're slower than the simplex algorithm. And the similar thing has happened recently in the question of primes. There are these tests that are used in cryptographic applications, tests to determine whether a large integer is prime or not. Well, we now know as a result of some graduate students in India that this problem can be solved in polynomial time. But again, the probabilistic algorithms that have been used to answer this question in the past, although not polynomial time in theory, are still more efficient in practice than the method discovered recently. So the question of whether something is polynomial time or not is a theoretical one, but doesn't necessarily correspond to practical reality.
Yeah, it's an excellent comment, and let me just add to this, just a caution that, of course, you should not have understood from my talk that all of complexity theory deals only with deterministic algorithm, with worst-case analysis, which means that there exists some unnatural examples on which an algorithm is slow. It only deals with all this. It deals with probabilistic algorithms. It deals with average case analysis, which is a typical behavior of algorithms like, for example, the simplex method. And, of course, there's a lot more to it because we need to solve these problems. And when we need to solve them, we study other notions of what it means to efficiently compute. So that was just a worst-case interpretation.
Saul, you'd like to add?
Yeah, I'd like to ask Avi a question to understand better about these zero knowledge proofs. You said that Alice can go to her chairman and convince him that she's proved the Riemann hypothesis without giving any details of the proof, right? And presumably she could go to the Clay Mathematics Institute, the same, and claim the $1 million prize. But
they have conditions.
yeah. So, well, the conditions are it has to be checked by several experts, so she could go around to all those experts and convince them equally, I suppose. How does she do this?
A few of you caught me in the tea room, and in 15 minutes I managed to explain the ideas of the proof of this theorem. But let me just say,
we could also say that we saw the P different from NP.
Yeah. If you did, you can.
If we did.
Yeah. Okay. Yeah. So let me at least, at the very least, explain what kind of proofs we are talking about when we are talking about zero knowledge proofs. They are proofs different than the published mathematical proofs you read in journals in two ways. One is that they are interactive, namely the person who is like Bob, the chairman in that case, who is interested in being convinced, is allowed to ask questions. So it's not just a written proof, it's an interactive proof. That's one thing you have to accept. So it's different form. The other way in which the notion of proof was changed in this setting, which is very important in cryptography, is you allow a tiny probability of error. Now, this is something which is totally unacceptable in mathematics, but in any life situation which I claim the mathematical enterprise is interested in, right? I mean, we know that when proofs are even published, they may have bugs in them, but never mind. At any rate, you allow a probability of error. Now, the probability of error that you allow in this kind of proof is arbitrarily small. Namely, Bob can decide that he wants it to be 1 in a million, or 1 in a trillion, or 1 in 10 to the 10. He would still be able to carry out this conversation and be convinced, as it were, beyond any reasonable doubt. Now, the way this, let me just tell you the two parts of the proof, without getting into detail how they are done. The first thing is you don't talk about the Riemann hypothesis. The first thing you establish, and that's the novel part, is that for some kind of mathematical statements, that I'll tell you what kind they are, for some kind of mathematical statements that don't look like the Riemann hypothesis at all, you can have this magical zero knowledge proofs. And the second part, which was known and follows from NP completeness, in fact, is that any mathematical statement can be translated to this special kind of statement because they are NP complete. Now, the kind of statements that you argue about are something that's probably familiar to all of you from the four-color theorem. The four-color theorem states that every planar map, like in geography books, can be colored with 4 colors. So to claim that a planar map is 4 colors is not a big deal, you know that it's true. So here's an interesting claim, and this is the claims that are being proven, that a planar map is 3-colorable. It's interesting because not all of them are. Some are, some aren't. So if I claim to you that this map is 3-colorable, it's non-trivial and it may be hard for you to determine by yourself, like the Riemann hypothesis. So the zero-knowledge paper shows how you can prove claims like this map is 3-colorable in zero-knowledge. It uses the special properties of map coloring, the combinatorial nature of this, in order to do it, and it uses cryptography to hide, to basically put on the table information that is committed to, but nevertheless cannot be understood. This is used in the construction, and I will not explain it, but you do it, and then you go to the NP completeness of this map coloring question to realize immediately that any statement like the Riemann hypothesis can be translated to one particular map. And if you happen to have a proof of it, it would translate into a legal coloring of this map. You don't need to worry about the real hypothesis. You translate it to this end.
Okay, this gentleman in the front has been waiting with his question.
I'd like to get clarification on Gödel's opinion and the speakers. One of the speakers said that axioms are self-evident truths, right? Like all men are created equal. So is the axiom of choice a self-evident truth? If, as I understand, we take the position that Gödel was a Platonist, that would mean that he would have to sit and wait for 500 years and then realize whether it's true or not true. So my question is, what is truth to you, and do you think that the axiom of choice is true or not? I asked a few months ago 3 mathematicians this question. Is ZFC true? And Solovey said yes. Shelach said yes. And Cohen said, my opinions constantly shift. So, which is Gödel's opinion and yours? Thank you.
I think also John Burgess could,
Yes.
since
You
John...
were looking at me, but I didn't know whether...
No, I'd like everyone's opinion.
Everyone,
and
I know that...
Professor Pfefferman included, of course.
John Burgess started out as a set theorist, so perhaps we can start with your response and then the other panelists would contribute.
About Gödel's position and my own, and Gödel's position is we have a concept of set, and if we think carefully enough about it, we will see it has these various aspects, one of which is certainly the axiom of choice, others of which are reflected in the other accepted axioms, and some of which go beyond the other accepted axioms, and some of which we haven't yet discovered.
Saul, what about the axiom of choice?
Just one terminological clarification, just like completeness, incompleteness, axiom. When we, in daily life, speak of axioms, we grant it the status of evident truth. But when logicians speak of axioms, they simply mean formal hypotheses for a formal system that need not be evident. So that technical sense of axiom is to be distinguished from the ordinary, everyday sense of axiom. The other is, were you asking about my own point of view about set theory and the axiom of choice? Yeah, so I don't think that, I'm not a Platonist. I don't accept the Platonist philosophy as an account of why one should accept set theory. I sure personally convinced that set theory is consistent, but not because it's based on some reality, but just it happens to be consistent. And there are other systems that people have looked at, like Quine's new foundation system that nobody thinks of as being justified in a Platonistic way, and yet probably is consistent. So consistency by itself doesn't say very much, so set theory could be very useful as a consistent system without being true. But there is an intuitive picture, I do agree, to set theory that justifies accepting it on the basis of an ideal conception of what a universe of sets should look like. And so there are good motivations, it seems to me, for accepting the axioms of set theory, including the axiom of choice, on that intuitive picture.
Speaking of set theory, we haven't heard very much about it today, and yet this was Gödel's, I think many mathematicians consider his work in set theory to be really his crowning achievement. You explained, Saul, the 2 incompleteness theorems. You gave us the proofs. Didn't take very long. This would have just not been possible with his work on the continuum problem. So could you tell us a little bit about his work? I mean, just a few statements, and also address the issue of why the undecidability of the continuum problem differs from the the statements in the incompleteness theorems in 1931. And is this something that or do you think they're different? The continuum problem and the ad hoc statements that Gödel proved independent.
Okay, I have an hour.
Well, I just wanted to get a little set theory in at this discussion, since we haven't heard very much about it.
Well, one thing about my 2-minute exposition of the incompleteness theorem, the first and second incompleteness theorem, shows that in terms of the kind of mathematics that's considered high class today, those proofs that Gödel gave are really pretty simple. They can be explained very easily to anybody with just a small amount of mathematics, a small amount of logic. If I recommended the book of Torkel Franzen, Inexhaustibility, as a good example. I mean, it's 100 or 200 pages long, which is much longer than it needs to be. As proofs go, it's simple. By contrast, but it shows that in order to prove an impressive theorem, you don't have to have a complicated proof. There are really impressive theorems that people didn't realize before that changed the world of mathematics in one way or another, and that's an example in that case. Do we have other examples? There must be. At any rate, that's a general claim, but I don't have.
Simple theorems that change the infinitude of the primes, I suppose. That's a pretty important theorem.
Okay, Euclid changed.
Nash equilibrium.
Nash equilibrium was not too hard. And yes,
but
got a Nobel Prize for it.
No.
Eventually. Yeah, but about his proof of the consistency of the axiom of choice, that
or
did
the
change the technology of the metamathematics of set theory totally. And it did it by showing that different kinds of models could be constructed for set theory in a very, very interesting way. And the whole post-war work on set theory really is based entirely on Gödel's proof, and it's gotten more and more complicated. It's as far as high-class mathematics goes in and of itself, whether or not you believe in set theory, it's really quite interesting, extraordinary mathematics. So Gödel really was at the start of a revolution there.
And the technical machinery for the time, I mean, someone mentioned ingenuity, that this was just an extraordinary achievement from that point of view. And it also gave you the model that you had to start with to arrive at the Cohen result. So in a sense, it achieved the consistency result, but then brought you very close to the consistency of the failure. I think I would like to not end this without asking Avi a question about the P equals NP problem. What if it turns out to be independent? What will that mean? And do you think there's a chance of that?
Okay, so yeah, of course I think there's a chance because we have no idea whatsoever, and that's one of the possibilities. I think it will be unfortunate, but we'll have to live with it. For me, the meaning of it will be that it will be similar to the meaning of P different than NP, because what it will really say is that, well, maybe there is an algorithm, or there is an algorithm out there that solves, let's say, these NP complete problems, all of them, very efficiently, but we cannot prove that it does. So it's basically useless as something that that we could practical thing. I just want to point out, and this is relevant to what we just discussed about the axiom of choice, both Gödel and Paul Cohen's work. Most people don't, I think, believe that P versus NP is independent, but there is some work on trying to prove independence results, at least weak independence results for the P versus NP question. And in some sense, it seems that it's a finite version of this axiom of choice question, and it does seem like some finite version of forcing needs to be used as a combinatorial tool if you are trying to prove it. I just remarked that we know today that some at least very weak but still non-trivial fragments of piano arithmetic cannot prove that P is different than NP, unless factoring is easy. Integer factoring is easy. So it's a pretty remarkable argument that shows that if within this limited set of techniques that live low down in the piano arithmetic, you could prove that P was different than NP, then inadvertently you would have found an efficient algorithm to factor integers. So it's a very intricate structure.
Okay, so this will bring to an end this segment of the program. I'd like to thank the speakers for their really excellent talks. And I'd also like to thank the audience for their participation. And on behalf of the speakers, I'd like to thank the Institute for arranging this wonderful tribute to Gödel. I think he would have been very pleased, especially with some of the more controversial parts of the talks. I've also been asked to invite everyone to the reception in Folt Hall, which takes place now. Thank you again.